Thank you so much. I appreciate any questions in the chat or during the talk, but I think the way is they're kept for the end. But today I'll be talking about firn hydrology. Hydrology of compacted snow on ice sheets called firn sits at the intersection of fluid mechanics, thermodynamics, and phase change in porous media. In the next 40 minutes, I will show how these processes connect, and then how I develop simplified models and move towards a mechanistic understanding of firn hydrology. About 3/4 of Earth's freshwater is stored in glaciers and ice sheets, but due to climate change, this usable water is being rapidly lost to the ocean. Greenland alone is losing about 264 gigatons of ice every year based on GRACE satellite measurements. And that leads to another problem, rising sea levels. In just last 3 decades, we have observed about 15 to 20 centimeters of sea level rise in certain parts of the world. Models show that the sea level rise is accelerating over time, here shown on y-axis. By the year 2100, the sea level rise estimates are somewhere in between 0.25 to about a meter based on best and worst case scenario. And that threatens 8% of world population, which is about 500 million people. Hydrology kicks in on ice sheets typically during summer when surface snow melts, and that meltwater percolates into this top layer of compacted snow called firn. There, it can either be stored as a liquid, or it can freeze to form barriers of ice called ice layers, or it can reach much deeper to these reservoirs called saturated zone or firn aquifers that can go laterally to join streams, and actually through cracks and crevasses may end up in the ocean, raising the sea level. This large-scale dynamics is governed by small-scale physics. If you put wet snow under microscope, you would see a 3-phase system comprising of liquid water, shown here in red color, air in white color, in between solid ice crystals, shown here in blue color. Models developed at such small scales, at millimeter scales, are not useful to solve problems at much larger kilometer scales. So we use volume average descriptions, such as moisture content, which is the volume fraction of liquid water in this box. Porosity being the volume fraction of the pore space in between solid ice crystals, and saturation being a ratio of the two. If saturation is 0, there is no liquid water present in the pore space. If it is less than 1 and greater than 0, we call it unsaturated. And if it is equal to 1, which means there is no air present, we call that saturated region. Unfortunately, we do not know how heterogeneities in firn properties, such as porosity, affect the transport of meltwater. In fact, models such as NASA's ice sheet system model does not consider most of this dynamics. If you go and take a flight to Greenland and dig a pit, you would see these bands, blue bands of ice called ice layers that do not allow water to go past them. These ice layers can span several kilometers, as shown here by this radargram. In fact, on a Greenland-wide scale, these ice layers are pretty ubiquitous, along with the aquifers that sit on top of them, as shown here in different shades of blue color. It turns out that these ice layers and firn aquifers are rapidly expanding, and they can potentially accelerate the sea level rise. In remote sensing community, these firn aquifers act as blind spots because they cause attenuation of signals. An ice layer can cause signal scattering. Furthermore, LiDAR measures the surface elevation change, which is not the same as mass loss. So to understand these remote sensing observations, we need to have a better physical knowledge of hydrology. Ultimately, understanding the dynamics of meltwater, including evolution of ice layers, is crucial to constrain their contributions to glacier surface mass loss, especially in a warming climate. This brings me to the outstanding issues that the community has identified recently. There's this recent community review paper published in 2024, and here I'm cherry picking some of the quotes of this paper to motivate this talk. The first issue the community has identified is a lack of physical understanding. Current firn models struggle to reproduce ice layers in firn, and they do not capture lateral flow. Furthermore, the interaction of meltwater with these ice barriers, ice layers, is not very well understood. And that is important because it contributes as a runoff from the ice sheet. Part of the reason is that hydrologic models struggle with modeling coupled saturated and unsaturated flow regimes. We call them variably saturated flow models. Next is the need for multidimensional model. What we are expecting is a multidimensional physics. We want to know what is the lateral runoff without really modeling the lateral runoff within the firn. So that is needed. There are several models which are able to do multidimensional simulations, but the computational cost is prohibitive for them. And most of the models available in the community are still rasterized one-dimensional models. So we need to reduce this computational cost. Ultimately, we are interested in reducing the large uncertainties associated with meltwater percolation process, such as refreezing, ice layer formation, and storage. And that brings me to the outline of today's talk. First, I will begin with a focus on meltwater infiltration and ice layer formation. I will begin with defining a large-scale, multidimensional continuum firn model called hydrofirn that I have developed. And then I will simplify this sophisticated model to come up with a unified kinematic wave theory. Using these tools, we will try to study ice layer formation and then move towards large scale and in multi-dimensions. In the next but briefer part of this talk, I will go more into the deeper region, the firn aquifers, where we developed a new vertically integrated model for aquifers in cold firn. And then we will try to pit these two models against each other, vertically integrated model against a vertically resolved or a higher fidelity model. Lastly, I will focus on the effect of temperature on firn aquifer expansion. And then I will end this talk with some take-home messages. So let's begin with infiltration and ice layer formation. Physics-based hydrologic models are based on this phenomenological law called Darcy's law, which was given by French engineer Henry Darcy. It says that the liquid water flux depends on the fastest decrease in total water potential. We call it head, and the units are in meters. This Q is proportional to gradient of head, and it has a prefactor, which is called hydraulic conductivity. Hydraulic conductivity is the ability of a porous medium to let fluid pass through it. The gradient of this total head is divided into two parts. The first is the gradient of pressure differences or pressure head. So at 2 points in space inside firn, there could be two different water pressures, and that can drive fluid flow. But the other is regular gravity drainage. So the flow would like to move in direction of gravity. If you take a handful of firn, you would see that there is liquid water in it, and this gradient of pressure head could be in any direction. It's a three-dimensional quantity, but the gravity is always going to be vertically downwards. And the flow will probably move as a vector resultant of these two components. If you plot the pressure head in unsaturated medium, it depends on the difference of pressures between liquid water and air, and we call that capillary pressure. Here is a standard capillary pressure curve, pressure head along with as a function of saturation. In hydrologic models, this capillary pressure curve causes a lot of problems, especially close to complete saturation, where saturation is going to go to 1. This gradient term blows up close to complete saturation, or if you increase the spatial scales. So our fix was just get rid of capillary forces and still be able to capture most of the physics. If we do that, we can now do large scale and without worrying about saturated region and unsaturated region. So now I will define our continuum model for large scale and multidimensional firn hydrology called hydrofirn. In this model, we have two conserved variables. The first is total composition of water, or in other words, total mass per unit volume of water in liquid form, shown here in blue color, the liquid water, and in solid form, shown in gray color. I cannot just have liquid water because if phase is changing, liquid water is really not conserved. So here the formula says density of ice times volume fraction of ice phase plus density of liquid water times volume fraction of liquid water. Since phase change is involved, we have to think about thermodynamics because firn can be cold. So the variable we'd like to use couldn't be temperature, because temperature at 0 degrees Celsius, you can have all ice, all liquid water, or somewhere in between. So we need a better descriptor of thermodynamic state. And for us, that is enthalpy. So here, enthalpy can be divided into three regions. For temperatures less than melting temperature, it's the sensible heat of porous ice. It's density of ice times volume fraction of ice times specific heat of ice phase times the cold content, T minus melting temperature. But if the temperature is equal to melting temperature, this term goes away, and then we only have enthalpy from the latent heat of fusion of liquid water. So density of liquid water times volume fraction times latent heat. But if the temperature is greater than melting temperature, you also have extra term from sensible heat of liquid water. Using composition and enthalpy, you can define all of the thermodynamic states or all of the thermodynamic variables of the system. For example, temperature and moisture content. Here on x-axis is composition, on y-axis is enthalpy. Enthalpy or composition goes from 0 to about 1,000. And if it is 0, that means it's all gas, but we are here somewhere. So say 600 or 700 kilograms per meter cubed. If the enthalpy is less than 0, we are in the first region, which is gas and ice. And there, the temperature is less than melting temperature. Think about a porous ice block and put that on a Bunsen burner. What will happen is you are supplying enthalpy to the system, and the temperature will increase. So in addition to gas and ice, you will also have liquid water. And we call that three-phase region, where the temperature is 0 degrees Celsius, unless you have one of the phases being melted, being it liquid water or the ice phase. So if you keep on supplying it heat, the liquid water, the ice will turn into liquid water. And once you cross this line, the liquid water is only the liquid water is left. All of the ice phase is melted. Similarly, for moisture content, you start with no liquid water, and the moisture content is 0. But as you supply heat to this porous ice block, you get more and more liquid water, and so on. The continuum firn model is basically conservation of composition and enthalpy. So there is a change in composition with time if there is a flux of enthalpy, or flux of liquid water, sorry. That flux of liquid water, when it moves in a certain section, is going to change the composition. And that volumetric flux of water, I will discuss it later in a second. The second conservation is of enthalpy, which says that there is a change in enthalpy with time if there is a flux of enthalpy. And that flux could be divided into two parts. The advection part, shown here in blue color, which is heat carried along with moving liquid water. And it's the same as what you defined previously. And then due to temperature gradients, there can also be conduction. So the next term is the heat conduction part. Q is defined from Darcy's law, which is what we discussed. In the unsaturated region, since we have neglected capillary forces completely, it's equal to the unsaturated hydraulic conductivity in the direction of gravity. So if it is vertically downward, it's a one-dimensional process. It's not a 3D process in unsaturated region. But as soon as you form these saturated regions where SW is 1, there you need to solve for total pressure and then use Darcy's law. And that could be three-dimensional. So I can talk more about this one-dimensional, three-dimensional numerical framework in the Q&A, but we developed this entire model and we call that hydrofirn. Next, let's try to simplify this model and really see if we really need to solve a numerical model, or can we just skip that part? To do that, we will make some assumptions to develop a simple unified kinematic wave theory. The assumptions are, we assume density of liquid water is the same as density of ice, rho. There is no heat conduction. The temperature stays less than or equal to melting temperature. It never goes above it. And the dynamics is just one-dimensional. For that case, we can think of simple problems with simple problems. And for that, we first need to non-dimensionalize our system. So to non-dimensionalize the composition, we just divide it with density. And the non-dimensional enthalpy is density, or enthalpy divided by density times latent heat of fusion. If we make these simplifications, we can solve simple problems. We call them initial value problem with a jump. Think about firn with two different states, say wet firn over dry firn, or dry firn over wet firn, compacted versus non-compacted, and so on. We call that top and bottom state. And for these simple problems, the system evolves due to movement of some waves. We use this technique from applied mathematics called method of characteristics, where we have developed this diagram. We call that hodograph plane, where on x-axis, again, you have composition, y-axis is enthalpy, and you see these different kind of lines, right? I think of them as roads. So the slow path here is the lines of constant flux or constant meltwater flux, shown here by dashed lines. And the fast path are the lines of constant porosity. And how do you solve this problem? The only thing you need to do is plot your top and bottom state on this diagram and connect it by following certain set of rules. If you do this sketching nicely, you don't have to run your numerical model. This is really your answer. We were able to construct 12 solutions for firn wetting, drying, formation of perched aquifers, and ice layers. I have a lecture video on YouTube. This theory is going to help us with three things. First, it can help us verify and validate numerical models. There's a bunch of them, as published in RETMIP paper in 2020 or 2019. It helps verify those numerical models. Secondly, it's a great way to understand what's happening inside your firn or snow. Third, it can be used in larger scale models, say Earth system models, which do not care about these assumptions, and you will still get an okay answer. I'll give you an example of how we can use this theory in real life. So think about a firn core from Greenland. Here's a snapshot that shows multiple layers in this firn core. The top layer is made up of 70% porous snow, and right below it is this ice layer and this compacted snow. Using this as a motivation, I thought about a double layer firn. I think of a firn which is 10 meters deep with two layers, both layers being 5 meters deep. So bottom one layer is 70% porous, very similar to snow. There's no moisture content, so it's zero initially, and the temperature is 0 degrees Celsius. And below 5 meters, the porosity changes to 30%. Moisture content is still zero, but the temperature goes to minus 20 degrees Celsius. And at the surface, there is a high melt event, such as rain, that increases your moisture content suddenly to 0.4. Let's see how will this firn evolve. And to do that, I will first solve it using hydrofirn model. Here, you are looking at the 10-meter deep firn with a jump at 5 meters. First in porosity, it goes from 70% to 30% with a jump at 5 meters. Moisture content is zero everywhere, and the temperature goes from 0 to minus 20 degrees Celsius at 5 meters depth. So let's see what happens when there is a high melt supplied at the surface. All right, I know the video was fast, but if we combine all of these 1D results, we can make a depth versus time contour plot. Here you're looking at contours for porosity in black or gray color, blue for moisture content, and red for temperature. And I know it's three plots, we will only focus on the moisture content here. When the melt event begins, a wetting front moves down with a constant speed. And as it reaches to this transition depth of 5 meters, this lower, less porous and cold firn doesn't allow this high melt to go all in, but instead it throws some of it away. And that is going to cause a bifurcation of this wetting front into two waves. One goes down, we still call it wetting front, but then there is a rising perch water table that goes to the surface, and these engulf a saturated region driven by hydraulic pressure. I haven't told you this before, but on this slide, all of the contour plots come from hydrofirn model, but all of the dashed lines come from unified kinematic wave theory. How? Just good sketching skills. Here, I'm showing the same hodograph plane I talked about. All you're supposed to do is plot your top, bottom 1 and 2 states on this hodograph plane in the first pass. Then if your wetting front is in top 5 meters, you have to connect the top and bottom 1 state. And when your wetting front is in the, when your wetting front has reached this transition depth, you have to connect this top and bottom 2 states. So this test helps us with 3 things. First, it shows that hydrofirn model is verified. Secondly, it tells us that our kinematic wave theory is legit. We sometimes don't need to solve using a computer. We can just do it using our nice sketching skills. Third, it tells us that to form a perched water table, we need high melt. In the community, we think that these ice layers are form or thicken when there is already a pre-existing ice layer. And during summer, there is melt water that basically collects on top of it during summer, and then that leads to formation of this perch water table, and it freezes during cold season. But there are several issues with this idea. First, these ice layers exist in regions where you never have high melt, so you never form these perch water tables. Furthermore, you can see ice layers forming in regions where there was no pre-existing ice layer. Then the question is, what is causing the first ice layer to form under low melt condition? And to answer that question, I basically went back to the more sophisticated hydrofirn model, and there, in one dimension, without any assumptions at this point, I assumed an idealized firn with porosity 0.5, temperature -10 everywhere in this firn, and moisture content being 0. And at the surface, based on conditions in Greenland, I assumed a moisture content of just 3%, more than an order of magnitude lower than the previous case. And we assume it for 4 days. Let's see how this firn will evolve if we combine all of the results. Here, again, you're looking at depth versus time contours for porosity in black color. And now I have combined moisture content and temperature on the same plot. So here, what happens is, again, you have a wetting front that moves down when you supply this very small or very low moisture content at the surface. It moves down. And at the 4th day, when we turn off the supply, you would assume that this liquid water will move down as a block, but that's not how it happens. You see another wave called drying front, which is much faster, and it quickly catches up with the wetting front. And as soon as that happens, the moisture content starts to go down. And when that happens, at that point, you could see that the heat conduction is becoming dominant, as shown by these diffuse temperature contours. We think that conduction at that point localizes the freezing to form a nice and crisp ice layer, which is a sharp reduction in porosity. Based on unified kinematic wave theory, we were able to find the depth of ice layer. And in that case, a scaling for depth of ice layer, and that depends on meltwater flux Q at the surface, initial porosity of the firn, initial temperature of the firn, and the duration of the melt event. So in this case, In this case, we were able to sort of use this theory to explain complicated simulations. But unfortunately, ice layers are not a one-dimensional phenomena. And we recently added another dimension to this problem. So in addition to the depth, we now have a length and a lateral dimension. So here you're looking at 10-meter scales. Again, moisture content on the top, porosity in the middle, and temperature at the bottom, with some realistic variation in porosity from dye to site in Southwest Greenland. And I'll talk about that later in this presentation. And now we supply melt in just a specific region from 5 meters to 15 meters. And let's see what happens if we supply the same exact melt for 4 days. Excellent. In this case, you form a nice and flat ice layer. And then there are, since this is localized, you see these end effects where you form a bucket kind of feature. Now, if I increase this surface moisture content just by 3 times, let's see what happens to the same exact firn. All right, so in this case, it's not a nice and flat ice layer. What could be the reason for that? If I scroll back, initially you would see that there is a wetting front that moves down with a nice and flat interface. But as it reaches this low porosity ice layer, at that point, it starts to form a perch water table because the surface melt is very high. And at that point, you would see that the fluid starts to move in directions other than gravity. It goes up, it goes sideways. And then when it goes sideways, it goes into cold regions where it freezes. And as it freezes, it forms these low porosity, actually impermeable layers of ice with an irregular shape. We call these irregular ice layers ice chunks or ice blobs. If we look at the ground penetrating radar measurements collected by my collaborators from Southwest Greenland, we do see these ice chunks below these topographic catchments. These are the regions where water can collect and local meltwater flux can increase, forming these weird patterns right below these catchments. In reality, meltwater content or at the surface is not exactly the more physically intuitive boundary condition. More realistically, the boundary condition at the surface is net thermal flux that leads to melting of snow at the surface. And then the other boundary condition is snow accumulation, which is measured in meter water equivalent per day. We just rescale the snow to equivalent height of liquid water. And then initial conditions in the firn are again porosity, moisture content, and temperature. Let's try to think about how this surface net thermal flux forcing affect your firn profile or firn stratigraphy. We take the same 50% porous firn at minus 10 degrees Celsius and apply sinusoidal thermal flux forcing at the surface, here shown as QNet. The left side is the case, we call it net zero thermal flux, where whatever is being supplied during positive or warm period is being taken back during cold period. So it's net zero if you take a time average of this surface thermal flux forcing. For this particular case, ice layers form in a bottom-up fashion. It penetrates the deepest first, and then it becomes shallower and shallower. And the reason for that is after every cycle, melt has to face a low porosity and cold firn. So it becomes harder and harder after every cycle. But then the other case is net positive thermal flux forcing. In this case, the average is greater than zero. And in this case, the ice layers form in a top-down fashion. It successively penetrates deeper and deeper into the soil. What this tells us is the climate conditions affect the firn stratigraphy, the chronology of these ice layers. Or alternatively, if you have an ice core, this pattern of ice layer formation helps us understand past climate variability. Now, let's use this and model actual data from Southwest Greenland. So there is this site called Die2 in Southwest Greenland. Samimi and coworkers went there and they measured the porosity on 24th of May 2016. Here I'm showing it in top 3 meters. Wherever you see a reduction in porosity is where you see an ice layer. So this is porosity, moisture content is 0 because the temperature stays between -10 and -15 in top 3 meters. And then there was an automatic weather station nearby, which was measuring the net thermal flux as well as snow accumulation. So in this case, you could see the red line showing the thermal flux with 2 big peaks, which are the high melt or high thermal flux events where you should expect some melting to happen. Snow accumulation has been nice, and you could see that it has been close to 0 in most regions. Now, here is the modeled porosity, moisture content, and temperature. So if you look at the porosity, you can see that there is a change in porosity as your wetting front moves down. The moisture content is really how the liquid water is infiltrating into this firn. And we know that the temperature there is going to be 0 degrees Celsius, so we just collapse 2 plots. So in the first melt event, which is close to 18th of July, here you could see that the surface elevation has changed, and we can our numerical grid is still at the top. So we are not tracking the surface here. Surface doesn't move unlike previous models, but surface can live within the domain, and we can supply boundary condition at the first surface cell. So here you could see there is meltwater infiltration, and then there is the second one. The black line shows melt percolation from an upward-facing ground-penetrating radar, which was installed at the same site. Here, in this part between July and August of 2016, you could see that the average of thermal flux is greater than 0. So similar to the case we discussed right before this, you have a summation of these 2 melt events, and then it penetrates deeper. Furthermore, we found that there is a new ice layer that forms at about 2 meters below the surface from our model based on this conduction and cooling idea. And it was also seen in firn stratigraphic measurements conducted by our collaborators. This is a one-dimensional problem, but let's take one more step and think about another dimension to this problem. So here we have a one-dimensional porosity variation, which was measured. To make a two-dimensional profile, since we don't have data, we assume a correlated random field. Here, it's again 3 meters deep by 2 kilometers wide. We can go to a larger length scale as well. And it's a prefactor whose value goes in between 1.1 and 0.9. If it is gray, then it's the same value as its vertical sort of value at that location. And we just added a horizontal perturbation to this problem. Correlated random field depends on 2 parameters. First is the amplitude. If you reduce the amplitude, the variation becomes gray, which means it's the same as a one-dimensional profile, just varying in vertical direction. There's no lateral variation. The other is correlation length. If you reduce the correlation length, the features become less connected. So you can see that there is higher variability, spatially as you move in lateral direction. So if we multiply these two and keep everything else the same as a one-dimensional problem, here is the money figure of this talk, where I combine this one-dimensional plot. The top 3 panels are the exact same as I showed on previous slide. So it's a one-dimensional depth versus time plot, but the bottom 2 panels show a 2-dimensional solution at the same time. So here you could see that it's top 2.5 meters versus 2 kilometers in the X direction. And let's see how this firn will evolve over time. So here you can see this black bar that tells you the time, and you can see that the meltwater flux or meltwater content is changing because of infiltration. And I will pause it here. The reason why I'm pausing it here is you can see that there is an initial melt event that lowers the surface, and that meltwater penetrates deeper, and it's a pretty one-dimensional process, all good. But even though the variation were not too much, you could see that that these ice layers are forming here. And here. And if I scroll down, this is the second melt event. The process is not one-dimensional anymore, even though the variations were very, very small, right? 90% to 110%. And you still form 4 impermeable ice layers in this firn that do not allow meltwater to go past it. And also, it causes formation of saturated regions. Since this is saturation, you can see that you form fully saturated perched aquifers. Now, if you look at the final distribution or final stratigraphy of this firn, this is how it looks like, the porosity field with 4 impermeable ice layers in it. If we reduce the amplitude, we get back to a one-dimensional variation where you don't see any of these impermeable ice layers. We move towards lateral homogeneity. And if you reduce the correlation length, the length of these impermeable ice layers shortens and you get more of them, and they are less connected. Ultimately, I'm interested in, does the melt make it to the ocean or not? And these sort of profiles help us understand why field measurements are important to understand the lateral homogeneity and heterogeneity of these ice layers. So this brings me to the next part where the melt has percolated deeper into this saturated zone we call firn aquifer. Firn aquifers are also pretty ubiquitous, even beyond Greenland. Here is an example of firn aquifer from Antarctica, where you can see a classic plume shape of this firn aquifer, with firn having ice layers and ice lenses. Based on this idea, we came up with a conceptual model of firn aquifer, where in this plot, which has depth and lateral directions, the gray region is undisturbed and cold firn, say at -20 or -30 degrees Celsius or -5. The light blue region is the temperate firn, shown here in sky blue color, which is firn which was invaded earlier in its history. It's now 0 degrees Celsius, but there is no liquid water in it. It's dry completely. And the blue region is your firn aquifer. All conventional models use this terrestrial groundwater equation for modeling firn aquifers. But the problem with this is, if you've been paying attention, this equation is derived from liquid water conservation. But liquid water is not conserved if there is phase change. So we went back to hydrofirn model equations. This is the same equation I showed previously. We got rid of heat conduction term, and we integrated it vertically from 0 to aquifer height, and came up with a nice and elegant extension to this groundwater equation, specifically for firn aquifers, where you have this extra term that takes care of residual liquid water trapping. If there is drainage from an aquifer, some of the liquid water still stays in the firn, and that is this term. But if you invade cold firn, a part of liquid freezes and forms ice, and we consider that imbibition or invasion process in this model. This firn aquifer model helps us account for refreezing and residual water trapping, and it reduces the computational cost as it decreases the dimension from 3 dimensions to 2 dimensions, or 2 dimensions to 1 dimension. Let me show you an example where I compare this hydrofirn model against our vertically integrated model. On this slide, you're looking at a firn aquifer. On the left, you're looking at the saturation, with blue being your firn aquifer with saturation 1. And outside this firn aquifer, the temperature is -30 degrees Celsius. Porosity is 0.7. And this firn aquifer is about 200 meters high and about 3 kilometers wide. So mind the aspect ratio. Everything blue on this slide comes from hydrofirn model, and everything red, for example, this dashed line, comes from vertically integrated model. On the right, the top panel shows the logarithmic ratio of maximum height of this firn aquifer, shown here by a square, black in color, hard to see. I'm sorry about that. With respect to its initial value. So that's that, and it starts from 0 because there's a logarithm of that. Then X max is the maximum horizontal extent, and I was not supposed to play it. Okay, well, X max is the horizontal extent with respect to its initial value. So you take a log of that. Last is the liquid water volume with respect to its initial value. So let's see how this firn will evolve over time. Oh, sorry. All right, so in about 10 years, this firn aquifer has expanded outwards. So its height has decreased over time. Its maximum horizontal extent has increased over time, and the liquid water volume has decreased over time. And that is because a part of liquid water is being frozen as you invade new pore space. This test helps us with three things. First, it validates our hydrofern model in 2 dimensions. For such multidimensional firn models, there haven't been a lot of validation tests, and this is an excellent test. Second, it validates our vertically integrated model, right? It's excellent that it can compare well against a higher fidelity hydrofern model. Third is the computational cost. Hydrofern model took about 2 hours to do this simulation, whereas the vertically integrated model took only 6 minutes. So it's better to use a vertically integrated model for a lot of different processes. Now let's move forward and try to solve a better problem using the vertically integrated model. Here, I'm assuming a domain of 1 by 1 kilometer with a porosity with these correlated random field again. I like to use that once in a while. And you're looking at the porosity contours averaged vertically. So here, white shows it goes in between 0.4, which is less porous, less permeable, to white being about 70%, very snow type when it is white. On the right, you're looking at temperature that goes from -30 on the left to 0 degrees Celsius on the right. And let's see how firn will evolve in this for the two cases. Here on the left, for the control, I am using a 0 degrees Celsius firn. So instead of having the temperature variation I showed on the previous slide, it's all 0 degrees Celsius everywhere. On the right, it's the same cold firn I defined on the previous slide. And to do this test, I'm assuming an aquifer height of 10 meters on the left side, and that would lead to an aquifer expanding from left to right over time. And let's see how this aquifer will expand. All right, if I stop it here, you could see that there is a difference between aquifer expanding in 0 degrees Celsius firn versus cold firn. In fact, aquifer is slower in colder firn because when you invade colder firn, a part of liquid water freezes, and that reduces your porosity and permeability. So aquifer is less conductive in cold firn. Secondly, if you lose liquid water, you are also reducing your Darcy flux, and that also reduces the rate of expansion. So now to summarize this talk, in the first part, I talked about meltwater infiltration and ice layer formation, where we developed a large-scale firn hydrologic model called hydrofirn. Then we simplified it to develop unified kinematic wave theory to understand physics and develop fast models. We discovered that ice layer formed due to localized freezing caused by heat conduction. Ice chunks form due to localized high melt events. Net warming may lead to successively deeper ice layers, and lateral heterogeneities strongly affect meltwater dynamics as well as ice layer formation. For firn aquifers, we developed a vertically integrated model specifically for firn aquifers. We found that our vertically integrated model compares well against higher fidelity hydrofirn model and is 20 times faster than it. Furthermore, we found that colder firn slows down the aquifer expansion due to meltwater freezing. With that, I'd like to first thank all of my collaborators on this slide, as well as funding agencies who made these research possible. And with that, I'd like to thank you all for listening, and I'm happy to take any questions.
Great. Thanks, Mohammed. That was really thorough. We'll open it up to questions. Again, please either raise your hand or put them in the chat, and we can handle them that way. All right, Alan, perfect.
This is always either a really easy question or a really tough question, but what next? Where is this going next for you?
Thank you so much for the question, Alan. So we have recently developed this larger scale model, and the hope is now to use it to do large scale simulations. So in the future, we would be using this model uh, to solve SMAP scale problems, say about 33 kilometer scale, or you can actually use it to do larger scale problems. So actually comparing that and comparing how much of the meltwater um, really goes to contribute to sea level rise? I think that is an important question. And a multidimensional model should be able to help figure that out. So that's first. Second thing is to make the model more sophisticated, add more bells and whistles, which are missing. So we don't have compaction right now in this model, which is very important if we want to do a multi-year process. So we are currently developing more tools and technologies in order to make this more relatable. So right now we can do one summer very nicely. In the future, we should be able to do multiple summers and do an actual spin up and be able to compare it against field measurement and remote sensing measurements.
Thanks. I see, Ravinder, you had a follow-up question. Do you want to say it out loud, or do you want me to read from the chat?
Oh, yeah, I'm on the move, so but I can still speak and just read whatever I wrote. So thanks for the very nice talk, Afzal. Um, how do you see this intersecting, say, some of the ice sheet modeling, where we either are interested in ice velocity predictions or I know we worked on calving, and we figured out that the firn layer changes how ice shelves respond and how rifts will propagate. So lack of these firn models is introduces uncertainty into at least the fracture prediction. But how do you see generally this fitting into ice sheet models?
Thank you so much. And that's a very important question. There are multiple ways. Uh, I think first is just altimetry to gravimetry conversion, how much of the meltwater is running off, if you're doing a watershed scale or a small scale versus large scale, and how much meltwater actually is refreezing versus moving laterally. We don't have to simulate all of it. Even if we come up with a fraction, say X% is stored, Y% is running off, and so on. I think that would be useful. That's first. Second, and that partly dovetails with your talk, and I was getting towards that. How about we connect this hydrologic model to a ice sheet fracture model, right? Here we can simulate the pressures. We know where perched water tables are forming. We understand how they're, what is the cycle of these perched water tables. So you have these cyclic loading as well as you have pressure profiles. Could you use them in your fracture model and be able to simulate fracture propagation? Because some of the melt will naturally go through these cracks and crevasses and end up becoming subglacial. Subglacial fluid. You have these channels below the ice sheet. The way we are introducing these is at the boundaries. So the second is to do a decoupled but yet coupled modeling of structure or ice sheet fracture and hydrology. The third is the most sophisticated, where you make a firn model that naturally integrates with an ice sheet model. And that is probably the last resort, and we should get towards that, right? How can you connect these firn models, which currently do not talk to ice sheet models? So for that, you have to include compaction. And the current work, people use compaction equation, but in reality, you're supposed to solve a Stokes equation. And I'm hopefully in 5 years down the line, if things go well, we should be seeing something along those lines. So that is the last resort where things are just seamlessly connected, the surface water, the subsurface water, as well as ice sheet. I hope I answered the question,
Yeah, great.
Ravindra.
Yeah, that perspective is very useful to hear. Yeah, thanks. And maybe you can work on the fracture stuff sooner. Yeah.
Sounds good. I'll be in touch.
Anyone else? Just pass along that Liz said, great talk. Thank you very much.
Well, could I ask a sort of side question, which
Of course, yeah.
is not on the direct topic, but I was interested in your comments about how you created a spatial variability for your firn characteristics for the porosity variation. Because as I'm sure you know, people in the field do grid measurements, but if you say have a 1 kilometer grid with spacings of 1 meter, 10 meters, 100 meters, kilometer, and so on, is there any way that you can see that you could use that kind of data, which is obviously very limited, in order to constrain the sort of random model that you're using as in your trials?
That is a great question and a very important question, Liz. How do we move from one-dimensional models and think about multi-dimensions? And
Yeah.
if I'm making a measurement at where I'm sitting, should I make the next measurement 10 meters away or 100 meters away or a
Yeah.
kilometer away? That is a
Yeah.
very important question. So the first variable I'm interested in is the correlation length. How correlated are these properties? If I measure something here, is it still correlated at 100 meters away? And if you make these grid measurements, I think you should be able to sort of back calculate using semi-variograms what is the correlation length. So that's first approach where you are making a grid measurements. The second approach could be how about using ground penetrating radar data and then ground truthing that with actual data at certain locations, say 10 locations. So Osha Rennerbaum, one of our collaborators, has been doing that close to Dai-2 station. So where and we are trying to use and leverage ground penetrating radar measurement along with ground truth to come up with a 2D or a 3D porosity field. So there could be two sort of ways I can think of. I'm sure there are multiple ways. So I think modelers and field experts have to come together to devise a controlled experiment that we can do to sort of come up with correlation length measurements. And that would be useful. The idea is not to use a multidimensional model. The idea is to understand what can we take from this multidimensional model and how can we simplify that and use in our bigger churning Earth system models, because they probably don't care about a lot of things that I talked about today. So I think it would be nice to sort of come up with correlation lengths and then see how much difference does it make if you plug them in a multidimensional models and at what scale. It's all a matter of scale, spatial scale as well as temporal scale. So to answer your question, there should be field measurements done, and there should be a nicer integration in between remote sensing measurements and field data.
I think probably, since it's not an ideal world, there's an awful lot of data around on spatial variability, as from surface radar, from actual measurements of density, and it's really in a sense, it would be nice to have some kind of process, if you like, of putting that together and seeing whether you could actually deduce a sort of a standard, if you like, that you could use. I mean, it wouldn't be the same in different parts of the ice sheet, but it seems a pity always to say, well, we'll have to do this in the future, and see if we could find a way of putting stuff together now.
I think that's a great point, and I think we should talk more about this because this is one of a big problem that we have now, which is restricting the hydrologic model predictions. So thinking about one dimensions to multi-dimensions is an important question, and I think we should talk more about this. I think there is interesting work that could be done along those lines.
Yeah. Thanks. Well, just one last comment. I'm sure you're also aware that there's a whole gang of American astronomers who are doing a grid across the top of Summit, Greenland, and they're very, very interested in density variations because it affects their neutrino telescope. So they might be making the sort of measurements that we need as well for their own purposes.
Interesting. I would love to look into that. Maybe I'll reach out to you, Liz, after
okay,
this, and we can
let's talk
chat more.
about it offline. Yeah.
Sounds good. Thank you so much, Liz. These are excellent points.
Hey, I have a question. I don't know if there's other people in line though. Can't see.
Yeah, go ahead, Mark.
Oh, this is actually John Neary. I'm in Mark's lab group, but we're all watching.
Oh, okay. Psych. Yeah, go ahead.
So my question is, on the models with the really large aspect ratio, we're looking at like a couple meters or a few meters depth by many meters sideways. Like, what's the boundary condition on the bottom, and like, is there a chance that stuff is leaking out the bottom of the model here, or over the time scale you're looking at? I'm just curious, what's the like how does this couple with the much thicker ice sheet as a whole?
That's a great question. Right now, I have not considered ice sheet in it, but the model can have an outflow. Currently, we are working on connecting this with impermeable ice layers. So there is no motion of ice in this model. Let me just clarify that. And that is something for the future work. For the boundary conditions, it's just outflow at the bottom. So liquid can actually go out of the domain. What people or what other models do is they assume once it's out, that is also called runoff, which is not exactly the case, right? It can do a lot of things if it is out of the domain. So one thing we are currently working on is making an unstructured, or not unstructured, but a non-uniform grid spacing mesh. So right now, I was simulating 5 meters deep, but once we have non-uniform grid spacing mesh there, we can do 20 meters, 50 meters deep, and still be able to resolve some of these features. So, and then we can go up to the ice sheet. But again, ice sheet motion is not considered in this work, and that is an excellent direction of future work.